Очень приятно. Меня зовут Nakajima. So that's the only Russian I know. So I switched to English. Sorry. It's a great honor for me to give talks here. So my title of my talk is geometric representation theory. So maybe you don't know what it is. So I first briefly explain what is geometric representation theory. So geometric representation theory is a study of representations of Lie groups or Lie algebras or some their cousins via geometric techniques. So Lie groups are manifolds, an example of manifolds, and it is simultaneously a group. So and the manifold structure and the group structure are compatible. So Lie groups themselves are geometric objects. So how to say? So of course, in the history of the study of representation of Lie groups, geometric techniques have been used. So, but here I emphasize the geometric representation theory. It's slightly different from the usual conventional approach to the representation theory of Lie groups. Or maybe I should say that maybe you know Borel-Weil theory or wild characters formula, which was which are geometric technique which have been used in the study of representation of Lie groups. So Borel-Weil theory says that you study some flag variety which have Lie group action. So for example, you consider projective line. So you have a group SL2C acts on the projective line, and you consider the holomorphic line bundle on the projective line, and its section, the space of its sections are representation of the Lie group. And using this geometric construction, and especially using cohomology group of this line bundles, you can say many things on representations of Lie groups. But today I talk today and on Friday, and next week I will give some different geometric approach to the representation theory. So instead of Dolbeault cohomology group, which I just mentioned, I use topological cohomology group, which is, if you have a topological space, you can define check cohomology, singular cohomology, and if you have a manifold, you can consider Drum cohomology group. That's different from Dolbeault cohomology group. That is more topological nature. So I use a topological cohomology group. But that is somehow a very different feature, because on the topological cohomology group, even if you have a smooth group action, that is forgotten. How to say? On the topological cohomology group, the group action disappears. You only get only discrete group action survives. And we are interested in the Lie groups, which is a continuous group. So we are not interested in discrete group. Somehow, so it's very, very strange at first sight that you use topological cohomology group to study those Lie groups. But anyway, I will give some example, and I hope you will. So in today's lecture, you see some how to say feature of this theory. And also, that's one of the interesting points of this research is that those representation appears as hidden symmetries on various modular space, which have origin in theoretical physics. So those kind of ideas are quite useful also in physics. So that's what I want to explain. So, but before going to the geometric representation theory, I go back to the usual representation theory. So this is section -1. So we go back to the situation where I hope you are familiar with. But anyway, so I use various notation later, so I start with familiarization. So I consider group G, which is SL2C. So sometimes I just omit the complex number C from the notation. So I usually only consider Lie groups over complex numbers. So this is just a 2x2 matrix with determinant 1. And I also consider its Lie algebra, which is just 2x2 matrix with trace 0. Then we have two-dimensional representation of the group SL2C. Just you consider C2 as a plane, and SL2C is a volume-free Zagmin transformation of the plane. So you have a natural action, and I usually take coordinate x and y for the plane. And also I consider x and y as a variable. And you can consider polynomial ring. So for polynomial rings is a representation of this group G. But if you want to have finite dimensional representation of G, so I'm interested in finite dimension. Today I'm interested in finite dimensional representation of the group G. Then I take Vk. So this is my notation is slightly different from Sergei's notation. So Vk is a space of homogeneous degree k. Polynomials in x and y. So if you know the Bourdieu theory, this is just the space of sections of CP1 of line bundle OK. Oops. So this has dimension k plus 1. And this I denote by Vk. And this is, I mean, it's just easy to count the dimensions. So it starts, so it has basis x from xk minus 1 times y, and so on. And the last one is y to the power k. So it is a k plus 1 dimensional. And it's also known that this Vk is an irreducible representation of SL2C, which just means that there's no non-trivial sub-representation of Vk. And also it's known that any finite dimensional representation of SL2C decomposes into direct sum of irreducible representation of this Vk up to isomorphism. And this result is known as a complete reducibility of the finite dimensional representation. And so complete reducibility just means it is direct sum of irreducible representation, and classification means that all irreducible representations are obtained in this manner. So this is a classical SL2 representation theory. And I need to mention a little bit about weight theory. So this space Vk has a basis. But this basis has some intrinsic meaning, which I want to explain. So first, so it's slightly better to talk. So first, I should say that this representation of G and the representation of SL2C are the same thing. So the algebra is just you can obtain the algebra by differentiating the action of the Lie group. Or I mean. So the algebra, from the Lie algebra, SL2C, you consider the exponential. It is an element in the group, and you use exponential. If you have an element x in the Lie algebra, exponential of t of x is the element in the Lie group, and you differentiate by t, you obtain an action of Lie algebra. And the Lie algebra is a vector space, so it's really easier to deal with. So we study mainly Lie algebra, but it's the same thing. Once you have a representation of Lie algebra, you can integrate the action representation of Lie group. Well, implicitly I use that the fact that SL2C is simply connected, but anyways, also if you go to some universal covering of the Lie group, you can always integrate the representation of the Lie algebra. So anyway, so it's a slightly technical manner. So we just don't distinguish Lie algebra and Lie groups. Now we switch to Lie algebra and take a basis. So there's a standard one. So it's usually denoted by E and F and H. E is the upper triangular matrix. The diagonal entries are 0, and F is a lower triangular matrix. And H is a diagonal matrix. So diagonal entry is usually 1 and minus 1. And they satisfy the relation, which I wrote here. A commutator of H and E is equal to 2 times E, and H of F is minus 2F, and E and F is equal to H. So these are defining relations of SL2C. So you can forget the geometric structure, and those SL2C is a Lie algebra generated by 3 elements H, E, F, and satisfy these equations. You can consider in that way. Then you can compute the action of the of these elements on the space VK, just differentiating the action of the Lie group. So this is exponential of T, so the unipotent matrix you get, and it acts on XY, and it naturally acts on the homogeneous polynomials. So in that way, you can calculate the representation of E as a matrix of this form. This is again upper triangular matrix. And H is a diagonal matrix, and the entries are starting from K and K minus 2 and so on. So it jumps by 2, and the final element is minus K. So this is the element E and H represented in the representation, represented in VK. Then the element y to the power k, or in this matrix, this is 1, 0, 0, 0. So E multiplied by 1, 0, 0, 0 is 0. So this is some distinguished vector. So it is usually called the highest weight vector. And the meaning of weight will be clear. And if you multiply H to the XL to Y minus YM, you just get L minus M. Well, L minus M is just one of these entries. So H times XL times YM is just L minus M XL YM. So it means that XL times Y to the M is an eigen vector of this matrix H. I mean, of course, this is diagonal matrix, so it's easy to compute eigenvalues and eigenvectors. But anyway, so this, if you return back to polynomials, this is eigenvector, and the eigenvalue is L minus M. And in the representation theory of this Lie groups for Lie algebras, those eigenspace is called weight space, and those eigenvalue is called weight. It's just the name. It's just the big, just the same as eigenvalue and eigenspaces. And so weights of VK is starting from K. Jump by 2, and you end up with minus K. And the largest value, K, is called highest weight, and the smallest value, minus K, is called lowest weight. So this is the usual theory of weights and the highest weight and the lowest weight for representation method. And Vk decomposes into direct sum of eigenspaces, that is called weight space decompositions. And also I introduced the so-called character. So character is a refinement of the dimension of the representation. So instead of just computing the dimension of the vector space, you can consider the generating function of the dimension of the weight spaces. So Q is a formal variable. So so this is a notation. So V Vk. So I usually write weight in the suffix, and this is weight space, and the character is the generating function, its dimension. And from this formula, in this example, it is just this polynomial which you saw in Sergey's talk. So in particular, so we know that the irreducible representation is just given by Vk, and k can be read off from this formula. So k appears in as the highest weight. So irreducible representations are determined by their highest weight. This is true for more complicated Lie groups, simple Lie groups like SL and C or SO and C or such things. And moreover, these characters are really refinement of the dimensions, and finite dimension representation are determined by their characters. So you may have, so this, for example, you take a three-dimensional representation. Three-dimensional representation can be irreducible over the direct sum of 1 plus 2. So that can't be seen, that can be distinguished from just only from dimension. But if you consider corresponding characters, then because of this finite information, you can easily check that you can distinguish direct sum and irreducible ones. So somehow the characters are most important, invariant for the representation, finite dimensional representation of these kind of groups, and even for infinite dimensional group characters, infinite representation of SL2, the characters are very important invariant. So anyway, this is the end of my review for the classical usual representation theory. But I pose some question. So these notion, these weights and characters and such things, depend on the choice of the base. So I start with this definition of weights by choosing a basis of Lie algebra. So of course, you know that on the vector spaces, there is no canonical choice of base. You just choose a basis and start something. But these weights and the highest weight and the characters depend on the choice of base. If it's so, then it's it's an artificial choice, and it should not be a fundamental object, and those theory of characters and weights doesn't quite make sense. It's not. So those. By the way, so I think I explained the next transparency. But anyway, so I first E and F and H are not the canonical, not the arbitrary basis. This is some as I said, this is a standard choice of basis, and usually not only for SL2, so we can consider instead, for example, G is SL NC. So in this case, you usually choose HI, It's 0, 0, 0, 0, 1 and minus 1. So this is ith entry, and this is I plus 1th entry. And EI is similar. So this is upper triangular, but you put 1 in the ith entry. And FI is just lower triangular. So usually we first take H to be something diagonal, and EI and FI to the upper or lower triangular ones. And by the way, so this E's and E and F are eigenvectors with respect to the this Lie algebra. This Lie algebra is a representation of the Lie algebra itself by the so-called adjoint representation, which just means you consider element of this element in the Lie algebra as a matrix acting on the Lie algebra itself as by this bracket, Lie bracket. Then we have this defining relation HE is equal to 2E and HF is minus 2F, which means that this E is a eigenvector with eigenvalue 2, and F is eigenvector with eigenvalue minus 2. So somehow, once you pick up H, then E and F are canonically defined. So similarly, so I think the choosing diagonal. So in this picture, for SL2C, it's not so clear, but for SLNC, HI and HJ commutes because those are diagonal elements. So choosing HI as a basis is quite natural. And then once HI are chosen, EI and FI are determined as a simultaneous eigenvectors. So in some sense, it's not a really artificial base, and it's quite natural base. But usually we learn when we study the manifold or the vector spaces. Base is just some choice, and it should not be some canonical fundamental object. But anyway, so those it is known that once you take those base coming from commuting elements, and you choose E and Fi's by some rule, then like eigenvectors, it's somehow those choice of bases are equivalent. And so the characters and the theory of weights, those things are independent of the choice of the base. So it's okay. But so in this way, people studied those representation theory. But I first learned this theory. It is really, somehow I still don't. I didn't like it at all, because that again the choice of base is a not fundamental thing, and it's rather strange that that kind of notion is very, very crucial in this representation theory. But I emphasize that the geometric representation, which I just start to explain now, this choice of basis is very, very essential. So you can't avoid. And in fact, I cannot really construct the Lie group, representation of Lie group directly. Only Lie algebra, SL2C or more complicated things appears, but I can always regard this as those Lie algebra generated by such kind of element with given with the defining relation which I just wrote. So this kind of presentation is really fundamental in the example which I will explain now. So that's somehow very, very, if you consider G to be some geometric object, and this is vector space, so the base, choice of base is something artificial, so it's a little bit strange. So now I really start the introduction. So I construct representation with S2C in some very, very strange way. So this is I first construct a two-dimensional representation. So I want to construct this two-dimensional representation as a cohomology group of some space. I mean, as I said, it's not a Dolbeau cohomology group like here. It's a topological cohomology group. Drum cohomology group, maybe you can consider. So far, I will only consider manifold, so you can consider topological cohomology group as a drum cohomology group. So what is the topological space whose cohomology group is two-dimensional? I mean, of course, you can say it's S2. But I prefer more simpler one. So that's just 2 points. So you may see, this is really trivial example you may consider, but anyway, I start with it. So to let M to be 2 points, I name it 0 and 1. Then it's a homology group. I prefer to use homology group rather than cohomology group. But it's, of course, this is a manifold, so you have Poincare derivative. So of course, 2 points is, too simple to consider to be manifold, but anyway. So this is, I only consider the complex cohomology group with complex coefficients. You can, of course, consider cohomology group with, for example, torsion with cyclic group coefficient, but that goes to representation on data space. I want to consider representation on complex numbers. So I consider the cohomology group with complex coefficients. Then I want to realize E and F and H as some operation on this cohomology group. And that is, you don't have much choice. So E, if you consider E to be mapped from 1 to 0, and F is mapped from 0 to 1, then you have the corresponding operators on the homology group. That is the most trivial one. And you can just take H to be 1 on this 0 component and -1 to be 1 component. And this H star of M has a natural basis. So you have a canonical element here and a canonical element here, and it is a natural basis on H2. And in this basis, from almost clear from the definition, E is upper triangle of this form, and F is this, and H. So H and EFH satisfy these SL2 relations. So this is obvious. So next, we want to construct a three-dimensional representation. So then it's a little bit more complicated, and you must consider. So of course, the first candidate is 3 points, right? Then you have a three-dimensional space, but but that is not really correct. On the SL2 three-dimensional space, so E is something written like this, right? You have entry 2 here. And this entry 2 must be explained in some way. Otherwise, you can't get this answer. And if you only consider, 3 points, then there's no way to produce 2. So that the reason why this 3 points is not correct. And in fact, this three-dimensional representation is a little tricky if you don't know this in the past. So I consider GR2, this is a Grassmannian of subspace in two-dimensional space. So usually to consider Grassmannian, you consider, you fix the dimension of the subspace and consider it as a manifold. But as in here, so I like disconnected spaces, right? Usually people in geometry, you could just consider connected space. I mean, you can study the space separately. That's fine. But as in the previous example, so I want to study some relation between different spaces. So this, I really use those disconnected spaces. So I consider Grassmannian of subspace in C2. Then you have 3 connected components according to the dimension of subspaces. The first one is zero-dimensional subspace in C2. That is just, I mean, zero-dimensional subspace is just 0, so it is a single point. And Grassmannian of one-dimensional subspace of C2 is just the projective line. I'm already considering complex numbers, so Grassmannian is also complex Grassmannian. And Grassmannian of two-dimensional subspace in the two-dimensional space is just, again, it is a point because SE, the subspace must be the whole space. And in fact, this is a natural generalization of the previous example. So if you replace this 2 by 1, so if you consider Grassmann variety of subspace in C1, so S in subspace in C1, then you have 2 choices. So S is either 0 or the whole space. So you get Grassmannian of subspace in one-dimensional space is just 2 points. So this is present. So now if you consider the total cohomology group of this variety, then first of all, so I by some reason which will be clear soon, I replace, instead of considering Grassmannian manifold, I consider its cotangent bundle. But as a homology, because the fibers are vector space, you can shrink those fibers, so the cohomology is the same. But in the calculation, you will see the difference. So anyway, the total dimension of the cohomology group, you can calculate it as a cohomology group of Grassmannian. Then you have one-dimensional space for the first one, and one-dimensional space for the last one. But in the middle, you have the P1 projective line, so it has 2 dimensions. So if you consider the total cohomology group, it is 4-dimensional instead of 3-dimensional. But there is a degree on the cohomology group. So by the reason which will become clear, so I take middle degree cohomology group of this cotangent bundle of Grassmannian, or by shrinking those fibers, it's a top degree cohomology group of Grassmannian. That is just H0 for the first component, and H2 for the second component, and H0 again for the third component. So you get the 3-dimensional space. And then I want to construct the operators E and matrix E and F and the H's by some geometric way, such that this gives these matrix. And in particular, I want to produce this number 2 in a geometric way. So H is rather, H is diagonal matrix. So somehow, and I want to make this to be weight spaces. Decomposition into connected components correspond to decomposition to weight spaces. So H is a diagonal matrix. H is automatically determined by each pieces. So I don't. Anyway, so it will turn. But if once E and F, I determine E and F, then H is automatically determined by commutation relation. So you don't need. Anyway, so H is diagonal, but those you don't need too much worry about this number too. So it will come up later, naturally later. So I give the definition of E and F's. So E and F are some generalization. So in the previous example, I consider the map from 0 to 1 and 1 and 0. So in this example, I also want to consider this operator something coming from the map. But you must do a slightly more sophisticated way. So instead of a map, I consider product of the of this first I only consider this first and second component. So I consider two product of those first and second spaces. So this is just the point times T star P1. And I consider projective line in the product. Of course, this is contained in the second component, but I want to consider P1 to be contained in the product of first and the second component. So something, once you have a map from X to Y, then you can consider the graph. So this is a submanifold in X cross Y. So in that sense, some submanifold in the product is a generalization of the graph. So in the first example, I can consider the map, but in more complicated, to construct a more complicated example, I need to consider more general kind of map, which is just given by graph of the submanifold in the product. So anyway, I consider this P1. In this particular case, it's map, but anyway, I consider this P1 to be product in submanifold in the product. And then I have two projections, so P1 and P2 projection into the first and the second factors. Then F is a map. I want to construct F as a map, linear map from this component to this component, and E to the map from the second component, second cohomology to the first cohomology. So there is a natural way. So once you have a cohomology class in here, then first I formulate it as a homology graph instead of cohomology class. So, but we have Poincare duality. So cohomology group and homology group are isomorphic. So if you have a homology class in here, you can consider first you consider it as a cohomology group, then you can pull back. Then from on here you use Poincare duality on here to consider it as a homology group instead of cohomology group. Then once you have a homology group, you can push down to the target, homology of target space. So this is the operation. Pull back. I just don't involve the Poincare duality in the formula. So I just pull back and push forward in this way. But I implicitly use the Poincare duality, as I mentioned. This is the map. This is the definition of F, the operator F. And for E, I change the role of first and second factor, and I put the minus sign here. So you have a homology graph here, then you pull back and push forward. So I define in this way. Yeah. Then I compute. So this is the first example. So I'd like to make I calculate slowly. So I apply F to be a fundamental class of the first space. First space is just point. So the Poincare dual of point is just 1. So the pullback of 1 is just 1. So you get projective cohomology class 1 on the projective. Maybe I write. By the way, so I don't know what is your background, so please stop me if something is not clear. So I consider the pullback of point class on here. So point class is the Poincare dual to 1. And the pullback of 1 is just 1 here. And then I apply Poincare duality here. The Poincare dual of 1 is 1 in H, 0 of Poincare dual is the fundamental class of P1. Then you push forward. So you get the class in here. So the final answer is P1. Then apply, so this is the operator F. So next I want to compute the operator E, which is the opposite direction. You start with E, P1. So P1 and pull back and push forward. So that is more complicated because this P1, so you must use Poincare duality on T star of P1. So the pullback of P1 is, first, this is a homology class. So you must apply Poincare duality to replace this P1 to be as a cohomology class. Then you pull back. But since this P1 is a zero section of this T star P1. So this is a line bundle, complex line bundle of P1. So once, if once you have a submanifold which is a zero section of the vector bundle, then its Poincare dual is the Euler class of the vector bundle, right? I hope this is some basic result in topology. So I hope you know that. So this P1 under the Poincare duality, I mean you must read a bit careful because T star P1 is a non-compact space. So for the non-compact space, Poincare duality involves cohomology group with usual cohomology group and the cohomology group with compact support. So you must be able to. But for any Poincare duality is for the usual homology group is mapped to cohomology group with compact support, right? So, for example, so that is easy to understand. On this space, you can push forward to a point that is integration, that corresponds to integration in the Poincare duality. But on here, if you consider cohomology group with arbitrary support, then it's a differential form which may be may divergent at infinity at the non-compact pieces. So the integration does not make sense in general. So that is not correct. So you must consider the cohomology group with compact support. Then here you can make integration. So anyway, this fundamental class of zero section is a Euler class or top Chern class. In this case, first Chern class of the vector bundle, which is just T star P1 itself as a vector bundle on the T star P1 by natural pullback. Then So P star of P1, P2 star of P1. So then you can put back. So P2 is in this case, P2 is just embedding of P1 as a zero section. So you have a Euler class of this vector bundle. So you restrict by the naturality, the pullback is a Euler class of the restriction of vector bundle on P1. But since I just pull back from here, pullback and restriction is the original bundle. So this is Euler class of this T star P1 is this P2 star. Then I need to push forward of this cohomology class. So I again use the Poincare duality, but on P1 instead of T star P1 here. Then I hope you know that the Euler class of this T star P1, this is in complex geometry, this is the canonical class. So this has a degree -2 on P1. So by the push forward, you get -2 here. So the entry 2, this 2, and I just go back to so by some reason I put this minus sign here instead of having 2 instead of -2. So anyway, those 2, we obtained this 2 in a geometric way as a Euler class, negative of the Euler class of the cotangent bundle of P1. So this is the correct geometric construction of this three-dimensional representation. So now I hope the generalization clear. So to construct VK, you just consider Grassmannian of subspace in the k-dimensional spaces. And I hope that the reason why I need to use the cotangent bundle of the Grassmannian instead of the Grassmannian itself is clear. Otherwise, I mean, I cannot consider the how to say Euler class of the cotangent bundle to consider it's 2 times twice of the point. And the generalization to VK is given by just considering T star of Grassmannian. Okay. So this is a disjoint union of Grassmannian of 0-dimensional space and 1-dimensional space and so on, up to T star of Grassmannian of K-plane. And if you consider its homology group is the same as the homology group of the base space, and if you consider top degree homology group of the space, that is always 1-dimensional. So in total, you have starting from 0 to k. So in total you have k plus 1 dimension, and you can define E and F in a similar way to get this VK. So this construction is in fact not so old. It was found by Ginsburg in maybe in late 80s or early 90s. I think. It's not so old. And if you want to generalize to instead of SL2C, if you want to generalize to SLNC, you consider what you have. T star of n step flag variety in CK. So n-step flag variety is just those flag of subspaces in vector spaces. But usually, if you consider the flag manifold, those vector space have distinct dimensions. But I allow those vector space to may have the same dimension. So this is my definition of n-step flag variety. Then from homology group of this M, you get case symmetric power of vector representation of SLNC. So this is again due to Ginsburg. So if n equal 1, n equal 2, then this Vk is a symmetric powers of the vector representation. So it's generalization. And if k is equal to 1, then the space is very, very simple. So I just check its dimension. So if k is 1, so I'm considering flag or n-step flag in one-dimensional space. But there's not so much choice here. Because so you start from zero-dimensional space. So up to I space, you get to the zero-dimensional space. And from I plus 1, you get one-dimensional space. That's the only case. So the only choice is this number I, starting from 0 to n minus 1. So in total, you have n-dimensional space. So this is a vector representation, natural representation by SLNC. So in this way, you get this. And the operator Fi and Ei is again defined by, in this particular case, these are a bunch of points. So again, you can realize it as a map. And if you consider this meaning of map, Fy increase those dimensions of the last Fi by 1. Then you get to the next example, and Ei decrease. I mean, maybe for this example, you should consider Ei plus 1. So Ei plus 1, you replace this one-dimensional space Fi plus 1 by zero-dimensional space. So this is the definition of Ei and Fi in this picture. And as in the case of generalization from Grassmann 1 to Grassmann 2, you can obtain the operator Ei and Fi on this more general example for n-step flag in CK. So you get this symmetric power of SLNC in this way. And the similar construction of the while group. So for type A, while group is just a symmetric group. It's a finite group. Representation of the while group can be constructed in geometric way. I mean, that is more, how to say, more familiar, because a while group is a finite group. It's a discrete group. So it's, I mean, realizing the representation of discrete group on the cohomology group of some space is more, how to say, more familiar concept. So anyway, this kind of representation of the while group, geometric construction of while group on the cohomology group of some space is known much longer. And it is the theory of the Springer representation. And the simplest example, which is just I don't remember which one, but it's a sign representation or a trivial representation. That is one-dimensional representation of the while group. Is realized as again kind of similar variety, which is that the cotangent bundle of flag variety. So then I considering again middle degree cohomology or top degree cohomology of the base. So this is again one dimension. So it just gives us trivial representation or sign representation. And the two constructions are very close because, for example, if you consider T star P1, I realize this is joint union of a point and T star P1 and the point. So this corresponds, this gives the three-dimensional representation. And each connected component corresponds to weight space of this representation. And it's known that this is weight zero space. H acts by zero. And weight zero space, you have an axiom of the wire group. And this representation wire group is the same as the wire group representation which appeared in Springer theory. So in that sense, two examples are connected. When did I start? Yes, how many minutes more?
You should make a break here.
Should I make a break here or what? Maybe let me see. Maybe, yeah. Then, so this covers only the algebra of this SLNC. So this is the so-called type A real algebra. And the generalization to other real algebras are not at all obvious. And I introduced some variety, which is a generalization of this kind of n-step flag variety. And I named it quiver variety. And its middle degree homology group is a irreducible representation of simple real algebra of type AD, or more generally, so-called symmetric Kac-Moody real algebra, which is, for example, affine real algebra. So and this quiver variety is no longer a cotangent bundle of some space. So that is somehow that is one reason why this theory is more difficult. Finding the geometric object to correspond to representation is more complicated. But that has some simple reason. So if once you have this kind of cotangent of something, the middle degree homology group or top degree homology group of base is one dimensional always. That is given by the fundamental group of the variety. So you get only one dimensional space. Then the representation you can obtain in this way is just must have all the weight space to be one dimensional. Such a representation is very rare. So for type A, you can find those kind of examples, but beyond the type A, such examples are quite rare, and in most cases, the dimensions of weight space is larger than one. So it means that the variety should not be a cotangent bundle of something. So I stop here and make a break. I briefly explain that how I construct a one-dimensional representation of the Y group, but I can construct also more complicated representation by some slight generalization. This construction will not appear in data, so you just listen once and you can forget. But anyway, so instead of considering the total, this is misprint. So instead of T star P, zero section G over B in cotangent bundle of T star GB, you just consider the so-called Springer fiber. So this is just, you have a map from T star G mod B to nilpotent variety, which is the famous Springer resolution. Then you take a point in the nilpotent element and consider its fiber. If X is 0, then T star, the inverse image is just G over B. And considering more general fiber, you can construct all other irreducible representations. That is, in general, not one-dimensional, more higher dimensional. And this mu inverse X have several components, and that is compatible with the fact that this wide group representation in general is not one dimension. So anyway, I go to, I think I will skip some part, and I will come back tomorrow. And I'd like to construct the next example, which is slightly different, but have a similar flavor. So I consider oriented C-infinity manifold, and I assume it to be compact for simplicity. So for non-compact space, as I mentioned, that you must be a little bit careful for Poincare duality. But here I only consider the compact space. So then you have the usual Poincare duality between the cohomology and the homology. So in the data from Friday, I need to study also non-compact space, but the compact space makes the picture simple. So I here assume X to be compact. And also I assume that X has no odd degree cohomology group. And the generalization to more odd cohomology groups is also simple, but for simplicity, I assume X has only even degree cohomology group. And I consider the symmetric product of X, which is just I first take nth Cartesian power, and I divide by symmetric group. So this is which I denote by Snx. That is nth symmetric product of X. So this is not manifold, because if some, so this Snx parameterize n points on X, which you forget the order. And some points collide, then it is a singularity in Snx. But the singularity is quite mild. That is just it is a Sn symmetric group is a finite group. That is so the Snx is a usual manifold divided by finite group. So it is very mild singularities. And in particular, the Poincare duality for the homology group holds. And if you consider the homology group over integers, then you must be a little bit careful for this finite group quotient. But for complex quotient, you don't need to worry about this. In that sense, you can consider this to be manifold, although it has a singularity. Then the question is that I consider all those n number of points. I don't fix the number of points, and I consider all the space simultaneously. And I want to see some structure on the direct sum of the homology group of symmetric powers, starting 0 point to infinity. I mean that 0 points just means just a single point. S0 of x is a single point, and S1 of x is x itself, and S2x is just 2 points on two unordered points on x, and so on. Then answer is that this is a representation of one-dimensional Heisenberg algebra, which I will explain soon, modeled on the homology group of base. So that means for each element alpha in the homology group of the base space X, I have an operator P alpha and Q alpha. And P alpha is an annihilation. In physical language, this is annihilation operator, and Q alpha is creation operator acting on this space. So annihilation operator decreases number of points by 1. Creation operator increases number of points by 1. So it's a map from H star of Snx. Annihilation is H star Snx to H star of Sn minus 1x. The creation operator is Snx to Sn plus 1x. Then we have relation. So I take two homology graphs, alpha and beta, from the base, and I consider the corresponding operator P alpha Q beta. And then I compute the commutation relation. Then the commutation relation is this is some multiple identity, and this coefficient is given by intersection number of alpha and beta in X. So that is this is a defining relation for the one-dimensional Heisenberg algebra modeled on this homology group of base. And it is also known that this space is a so-called irreducible representation. Heisenberg algebra has only one irreducible representation, and this is this representation. And HSN S0 So as I said, this is a point. So this is C, and this is the canonical one element. Is in this physical language, this corresponds to vacuum vector. And any element in this space can be constructed from this vacuum operator by successfully applying the creation operator. So this is the structure of the representation. And I want to construct these P alpha and Q vectors in a geometric way, and I want to check the defining relation. So this is a construction. So this is a slight modification of the previous construction. I consider in previous construction, I consider the product of cotangent bundle of Grassmannian, and I introduce some submanifold in the product. But here, you slightly modify. I consider a triple product instead of two products. That is the reason why these operators are decorated by the homology class of the base. So anyway, so I consider triple product X and SNX and SN plus 1X. Then in here, there is very canonical I mean, of course, this is not manifold. You can not say that this is a sub-manifold, but up on the homology group, you can consider this to be sub-manifold. So I consider some canonical sub-manifold in. So I say the sub-manifold, although it's not a sub-manifold, it's in strict sense. But anyway, so I have canonical sub-manifold Z, which is given by this formula. So this is a triple X and sigma 1, sigma 2. Sigma 1 is n tuple of unordered points on X, and sigma 2 is a unordered n plus 1 points in X. And I have one another point X, small x. So the natural condition to put is just this condition. So sigma 2 is equal to X plus sigma 1. That means that the sigma 1 is n tuple of points. I add one extra point X. That comes from the first component. By the way, so I didn't. There is some symplectic geometry in behind, and many things. So T sub Grassmannian is a symplectic manifold, and those total space, the base Grassmannian, Lagrangian submanifold in the symplectic manifold, and similarly, so I don't assume X to be symplectic manifold, but if I assume X to be symplectic manifold, the symmetric power is again, I mean, of course, it may have singularity along those diagonals, but there's a kind of general symplectic manifold in general sense, and those triple product is again symplectic manifold, and Z is a Lagrangian submanifold in the symplectic manifold. So in particular, you compute the dimension of Z. So dimension, so you can move sigma 2. Sigma 2 has n plus 1 times dimension X choices, parameter families. And if you fix sigma 2, then the remaining choices, you just pick up 1 point from the sigma 2, that is X, and you have remaining pieces sigma 1. So once you fix sigma 2, you only have finitely many choices. So that for the dimensions, you just need to fix the sigma 2. So it is n plus 1 dimension x, n1 plus 1 times dimension x. And if you compute the total dimension, so you have x and snx, that is also the sum of dimension is again n plus 1 times dimension x. So this dimension of z is just half of the dimension. And as I said, if x is symplectic manifold, then z is a Lagrangian subvariate. Then somehow, if you shift the degree of the order cohomology from the you instead of usual degree 0 to be the degree 0, you shift the degree by half of the dimension. So, but today you don't need to do so. I plan to explain that in previous screens, but I skip it. So you just forget this meaning of this half. So anyway, so I forget those. I don't worry too much about those degrees, degree of cohomology groups. So anyway, I pick up class alpha from the homology group of base, and I consider its Poincare dual, and I put back to a cohomology class on Z, and I again take a Poincare duality to consider the homology class on the Z. So then I define operator Q alpha and P alpha in a very, very similar way, just pull back and push forward. But the only difference is that on the middle, on Z, you just take a product with this homology class Px alpha. That is the only difference. The P alpha and Q alpha are very similar, so just to change the role of Sn and Sn plus. So you instead of pull back from the first factor, for P alpha, you just pull back from the second factor. So then you get the operator in this way. Then I need to check the relation, defining relation of Heisenberg algebra. That is written here. And maybe I go back to the so the original defining relation so original defining relation was this one. And so in particular, alpha and so this is the intersection pairing on X. So if alpha and beta are not complementary dimensions, so then this automatically vanish. So it's not interesting. I want to check an interesting relation. So I pick up alpha and beta to be the first non-trivial case, namely alpha is which? Alpha is the fundamental class of the space, which is Poincare dual of 1. And beta is the point class. So this is H top of X, and this is H zero of X. Then in the intersection pairing of alpha and beta is just to give just 1. So here this alpha beta is 1. And in fact, you can show that of even more general homology class, you can somehow reduce this case. So it's enough to consider this case. And I take arbitrary homology class in the symmetric product, and I want to compute this commutation relation. I want to check this computation. And so this is this has a very, very simple geometric proof for this. So I consider C is a homology class. maybe I write the defining relation again. P of alpha is x, and Q of point and this is P of x, Q of point minus Q of point. So this is a commutator. And I apply this operator to C. So in this case, C is just this represented by 3 points. This is H0 of S3 of x. I mean, you can take arbitrary class, but this shows the essential point of the proof. And you can reduce it. Again, you can reduce it to the computation in this case. So this circle represents x, and these 3 points is some element in here. And so I have a homology class beta, which is a point. So, and I pick up a representative of this class, which means that I have some chosen preferred point, which I write in red. I have preferred point in the space. So then I compute the operator PQ applied to this class and QP, and consider the difference of PQ and QP applied to this class. That is drawn in this picture. So I first apply Q. Q is a creation operator, and it is colored by this by point class, which means that so this is mapped by this is Q of point int H0 of S for x, which is just you also. So these 3 points are correct. This is the first 3 unordered points in the x, and I want to have 4 points on the x that I include this point. This is the operation Q point applied to C. So that is the middle, which I draw a figure in the middle. And then I apply the Px, that is annihilation operator. So this 4 points. So and the annihilation operator is colored by the total cohomology class. So in concrete, it means I can remove 1 point from those collection of 4 points, but I can remove any points. No particular preferred points. So this cohomology class is a combination of four cycles represented by those pictures. So in this collection of 4 points, I can remove any of those points. So I get four classes. What one? This one. Right? So there are the 4 choices. So this is a composition of P and Q applied on this class. Then I can do the same thing in the opposite order. I first remove some point, But here, this preferred point, chosen point, is not included in collection C. So to remove some point, I only have 3 choices. So this is a choice. And then after removing 1 point from C, I add this red chosen point. So I don't draw. So this is just P, and I don't draw the figure for Q applied to P. But anyway, so just you just replace this red point by black this X point, and compare the difference of the two answers. And the answer is the only difference is 1, which is just by giving this first adding this chosen point, and then remove the same point. So that this is the only. And because we add the chosen point and then remove the same point, this is the same as the original one. That means this is the class C. So that just means commutator of P and Q is identity. So that is the proof of this relation. So on Friday, I will explain slightly more complicated examples that is called Hilbert scheme of endpoints on X, and I consider its homology group. This is so-called Hilbert scheme. So Hilbert scheme is how to say, this is some more fancy version of the symmetric group of X, and it is larger than the symmetric power, and its homology group is larger than homology group of symmetric powers. But the structure is very, very similar. On here, I will construct a representation of infinite dimensional Heisenberg algebra. That is, instead of this relation, I get Pm of alpha and Q. So for each positive integer m, I have operator Pm alpha and Qm beta. The commutation relation is -1 to the m -1 to the delta m plus n 0 identity. So the algebra is very, very similar to this example. Instead of you just color the operator by cohomology class, you can color the operator by simultaneously by the cohomology class on the base and also by integers. So you have, in some sense, you have also higher mode operators on this degree 1 Heisenberg operator. So this is I want to explain on the Friday, and maybe I will prepare some several notion which I will use next week. So I stop now for today.
Thank you very much.